In part one of this exciting program, we learned 4 key points on interpreting radiographs based on visual perception and brain functions. In this section of the series, we are going to cover more key points and help you see like you've never seen before. Let's get started. 2 aspects of how our eyes and brain function that have a huge impact on radiographic interpretation are the phenomenon of visual search and the efficient smoothing of intermittent visual signals. To understand this principle, let's begin with an example. Take a look at this image and count the number of large dots. How many did you count? There are 8 dots present. Our eyes can quickly identify this size difference. Let's do the same experiment with another image. How many larger dots do you see? The answer is 5. Why is it more difficult to count the dots in this image? The dots are easier to count in the first image because the dots are big enough to be seen by your peripheral vision. Your peripheral vision then draws on your fovea, the area of acute vision on the retina, to the larger dots, and the dots are clearly seen. In the second image, the dots are not large enough to trigger a response from your peripheral vision. They do not attract the fovea that is moving at random, and dots are missed. Key point 5. Areas of radiographs that are only slightly different from their surrounding opacities may get overlooked if we are not making a conscious effort to direct our area of acute vision to all areas of interest. When we look, we feel that we see everything in detail, but we don't. The size of your acute vision is about the size of a dime, at 60 centimeters, the distance one might typically view radiographs. Every time your eye moves, it focuses on an area no larger than the size of a dime. Our eyes constantly move and jump from one part of an image to another, so we see in detail only the size of a dime. The rest of the image that was not seen by the fovea is completed by the brain. To better understand this principle, read the first few lines of this text. Notice how it seems as though you can clearly see every letter and word in that line? Now, fix your eyes on one letter of a word in the middle of the slide. You will realize that you only can see a few letters in focus. However, the instant you begin reading, the slide looks completely in focus. You can read quickly because your brain reconstructs the words based on just a few letters and word length. This makes you think that you have looked at each individual letter and word. This is hard to believe because it's counterintuitive, but the following exercise should convince you. Read the following sentence twice. Now, count how many times the letter F appears in this sentence. How many did you count? When we ask a group of people to do this exercise, the answer varies between 2 and 7. The correct answer is 7. While you were reading, your eyes were making jumps across the screen. Your brain was making assumptions about the words while you were counting, and you may have missed the F's from all of the ofs in this sentence. This is because your previous knowledge allowed the brain to jump over the ofs. You can try and control the jumps that your eyes make, but you are so used to skipping over ofs when reading that it is difficult to keep your brain from doing it. If we have a difficult time counting the letters in a sentence, it is easy to understand how we can miss radiographic lesions. Viewing radiographs is very similar to reading words and letters. Our eyes view pieces of the puzzle, and our brain fills in the rest. Unless we train our brain and eyes to focus on every critical area, the image we formulate in our brain may not be accurate. When we first start to read X-rays, we take a lot of time and pay attention to each, but when we become more familiar, we begin to diagnose more quickly. This can cause us to jump to conclusions, feeling that we have perceived all of the information on the X-ray. However, most of the information that we see was filled in by the brain and the previous knowledge gained from interpreting other radiographs. Key point 6. The area of acute vision is a lot smaller than we recognize. Remember the dime. Remember the dime strategy says the only thing you can see in detail is the size of a dime. So always have the dime in mind. Let's look at this X-ray and apply this process. One example is rib fractures, which are commonly missed. Because we have the impression of seeing all ribs with just a few eye jumps, most people are satisfied with their search and move on. To find rib fractures, you must look at the entire length of each rib in multiple jumps the size of a dime. By looking at dime-sized areas along the entire X-ray, you will help prevent your brain from filling in missing information and jumping to conclusions. In addition to the dime strategy, it is important to ask the right questions because the questions we ask ourselves determine what we focus on. Trying to draw conclusions from all of the varied information available on an X-ray can be difficult and lead to errors. You need to learn to focus on questions that truly have high predictive values. To help understand this principle, let's look at this X-ray of two flashlights. Which flashlight is on? This question is not the best one to ask because it does not directly focus your attention on the area providing the answer. This is why it is important to ask the right question based on the anatomy and physiology of a flashlight. You must understand that in order for a flashlight to be on, the electrical circuit must be closed. You must know what part of the flashlight opens or closes the circuit. Then you ask the question, is there contact where the switch closes or opens the circuit? Doing so focuses your attention to the switch, and as you can see, the flashlight on the left is turned on. This line of questioning narrowed your focus on a finding that has a high predictive value that the light is on. When examining a particular anatomical region on a radiograph, simultaneously ask questions that, if answered affirmatively, would have a high predictive value for a particular disease or condition. If the predictive value of an observation is low, don't spend time on that area because the information is useless. Instead, stay focused on asking questions and looking at areas with high predictive values. Key point 7. Ask yourself questions that have a high predictive value. Disregard questions that have a low predictive value. Here's an example of a question with a low predictive value. When evaluating thoracic X-rays, mild to moderate changes in the apparent size of the heart have a poor predictive value because the heart and the patient and the size of the thoracic cavity are all constantly moving and can vary in relative shape and size. Pulmonar veins and arteries, as well as the left atrium on the other hand, have a high predictive value because their size and shape are more consistent. If the pulmonary veins are larger than the arteries, and if there is a left arterial enlargement, heart disease is very likely. Let's review the 7 key points we've learned in this program. Key point 1. Always remember that our eyes and brain are poor at interpreting size and length. Key point 2. Our eyes are very poor at estimating absolute brightness. Mock lines will deceive us into inappropriate diagnoses unless we are aware of them. Key point 3. We must retrain our brain to understand the language of shadows, including the effect concave and convex objects have on radiographic opacity. Key point 4. Our brain draws quick conclusions based on previous experiences and what is expected. Sometimes these conclusions are inaccurate. Key point 5. Areas of radiographs that are only slightly different from their surrounding opacities may get overlooked if we are not making a conscious effort to direct our area of acute vision to all areas of interest. Key point 6. The area of acute vision is a lot smaller than we recognize. Remember the dime. Key point 7. Ask yourself questions that have a high predictive value. Disregard questions that have a low predictive value. In the next part of this program, we will teach you a strategy to read thoracic radiographs based on the principles reviewed in this section and, hopefully, help you see like you have never seen before.